Hey everyone, so let's now use our RBD material fracture to shatter glass. And it will look like this in the end. We have a projectile and that shoots through our glass and smashes it. That's the goal. So what I have prepared here in my clean version is of course a glass geometry with a little bit of thickness, the frame, there we go. And then we have here a projectile that is hand animated. There you go. So you might already guessed it, we will use that as a static object, not an active object, and this is why we hand animated it. So let's go with this. So first of all, of course, we want to shatter our glass geometry with the RBD material fracture, of course. It will instantly start calculating the concrete fracturing, so we can stop that if we want with escape. And then we switch to glass, and already we actually get something. But the first problem we will notice is when we look at our projectile, and move it to roughly the moment where it hits, you can see that the impact point, of course, is not matching with our geometry. If it is, then it's a pure coincidence. So let's make this actually a bit worse by going into the RBD material fracture, impact points, and maybe change the scatter seed so that we're sure that it's completely wrong. So what can we do here? We know how to solve this problem because we have the fourth input here, our extra Voronoi points, impact points, and that is actually what we want. We want to add a point here to define where the shattering should happen. So what we could do is we just use an add to create a single point somewhere in space, put this in here, and then manually set it where we want it. Where is it? There it is. Well, first of all, as we can see, it is not using it. So let's make sure it actually does. And we can do this by activating input points. There we go. And while we add it, let's disable the scatter points. We don't need the random ones. So again, now we can, when we look from the right angle, find the perfect spot by hand, maybe with this space 3, and there you go, perfect. Now you can totally do this and there's nothing wrong with it, but since we try to be more elegant, what we could also do is we could figure out where our projectile will actually hit the glass. This is especially useful if you know that the incoming geometry might change because maybe the animation department will give you a different result at some point. So what we could do, for example, is we could use our projectile here, find the moment it hits with a time shift node. And this is currently at, let's say, roughly frame 1010. So something like this, maybe actually one more. Yeah, okay, doesn't matter because it doesn't hit it. And now we want to have the center of this. And one way of doing this, for example, is using an assemble to turn the whole thing into a point. I do this all the time. You could even, if you want, use then an add node to make sure that you delete the actual geometry and only keep the point that is representing the geometry. So out of the assemble comes a single point. And to really show this, you could use an add node and then delete geometry, but keep the points. And there is our point. And now what we will do is we just use array node to stick this point to our glass. So this is what we want to change. So the point is the first input and the glass is the second. And then you could go either with the minimal distance, or if you really want to be super precise, you could use actually the velocity of the point with a point velocity, let's say. You could calculate the velocity and then you take that velocity as the project rays by setting the direction from normal to attribute, and then you could here use V if you really want it. Now in that case, of course, you wouldn't need a time shift because you want to calculate the velocity. So the setup would look a little bit different, but you know, they get the idea. In our case, we're lazy though, we just take the minimum distance, and what happens now is that the sphere turned into a point will be projected to the closest point on the surface, and there is our point that we need. To prove that, let's quickly change the position a little bit, and you can see the impact point is actually following our sphere. So this is a nice approach to this. Okay, so now we have the actually impact point procedurally generated, and this we can use as the impact point in our simulation. And voila, we have now the correct impact point for our sphere. And you can see how the impact point is actually following. So let's now make our fracturing a bit nicer actually. So let's now just throw this into an RBD bullet solver and see what happens. Because as you know, I'm a big fan of just trying out step by step what we have instead of throwing everything at the simulation. after setting it up. So first of all, okay, this falls down, which is good. Nothing is exploding or something. And to test it further, let's for now add under collision a ground plane just to see how it behaves. And yeah, it falls over and then it, wait a minute, what's going on here? When we run this, it falls over, starts to move, and then it stops all of a sudden. Ah, that's weird. Where have we seen this before? Now, of course, as we know, that's a common problem with the sleeping function. So you can either turn it off completely under advanced bullet solver and by setting the sleeping time to 0, or you go into properties and then under sleeping here and decrease the thresholds so it doesn't happen that quickly basically. But in my case, what I want is to turn it off completely. And now when it falls over, it actually is falling. Okay. This is what I wanted. I wanted to see how it behaves when it hits, and you can see it does not break apart, which is a sign that our constraints are too strong. So let's fix this in the RBD material fracture. And the constraints, there is our glue constraints, and it's set to an unbelievable 10,000 radial strength and 40,000 concentric strength. So this is insane, and it will definitely create problems later on if we leave it at that. So maybe let's lower this to 1/10 for each, and let's see what happens, even though we have to wait a little bit. It still doesn't break, so let's lower this further. Okay, now it breaks apart, which is a good starting point. We might have to adjust this later on, but at least now we have something where we know it should break apart. Also, again, it makes sure that we basically see if anything behaves weirdly. So if those pieces would, jump around or move as one piece, then we know there's something wrong in our setup. Now let's actually look into how to set up what we actually want. Now, the first thing we don't want is that it falls down and falls over. We want it to stay in the frame that we saw. Your first instinct might be to take that frame as a collision object and then keep it inside of that way, but this will create a couple of problems, because if we try this, up here is our frame and we put it into the collision object. Again, be careful, the input for the collision is the second from the right. Don't take the guide sim, but the actual collision geometry input. Basically, what you can see here, if you look closely, is you would start already with collisions, and this is generally not a good idea, especially not if this is your way of keeping things in place. If you would try this now, you can even see that it will ignore the whole thing. So it's not even a working solution at first. The reason should be obvious when we look at the visualization of our collision shape of our collision geometry. And you can see, because of course by default it's turned into a convex object, even though it's clearly concave. But even if we would turn this around and under collision from a convex hull to a concave one, we would, as you can see, create problems, because it would again instantly find collisions and the whole thing will not work. So how do you solve this problem? We already know how to solve this. The best way of keeping something in place is to simply deactivate it. So what we want to do is we want to deactivate all the pieces that would be basically tied to our frame. And to do this, we use our active attribute, of course, which reminds us we should probably use an assemble node here. Currently, we are not working with pack geometry, but I would recommend it. So let's pack it. And the name attribute currently comes from the RBD material fracture. So let's make sure that we're not overwriting this. So of course, in the assemble, make sure that you're not creating a name attribute on top. So we should see that the name of all those points that we just created, the packed points, should be the same as the pieces coming from the RBD material fracture. So the workflow now to deactivate the outside pieces, we already know. So first of all, we basically deactivate everything by setting the integer attribute active to 0. Let's actually call this active 0. Then let's use a group to define what pieces we want now to activate. That's the easiest in this case. So it should be a point group. Let's call it active group. Let's go with a bounding region. And here now we can define what we want to activate. Yeah, maybe something like this. Depends, of course, on your case. Feel free to change it to whatever you want. Maybe we would need a bit more pieces. Actually, let's quickly do this so that we have more pieces on the edges. Yeah, maybe something like this. And now let's double check again. And it's, as you can see, we now have a bit more pieces to play with. So let's use that. And then we create a new point wrangle, of course, where we activate all the pieces in our active group. And if we run this, we should see that the whole thing should just stay the way it is. And that seems to work. Now I know the whole time the projectile is running through the screen and we haven't used it yet. And that is actually the next thing we want to do. So instead of using the frame as a collision object yet, we will first use our projectile here. Again, the reason we use our projectile as a static or a passive object is that it should not be influenced by the impact. We used this workflow before. So let's make sure we're not using the time-shifted version, but the actual geometry. And thankfully, since it's a sphere, it's already convex, so that's fine. So let's go into the collision geometry. And here you can see in blue, it showed up now. By the way, I changed the collision from convex hull to concave. So let's go back to convex hull. I think that's a good idea because it is convex. And now if you press start, we can see nothing happens. Why is that? Our sphere is not moving. And of course that's because the animated collision type expects our sphere to be packed and animated. We could switch it to deforming, but we've seen that would usually get worse results. So let's quickly fix that. And we just have to pack it first. We could just steal our assemble here. Again, we can't use the time shifted version, so we have to use a copy. Maybe you can clone it or something. But that by itself will not help because this is not yet an animated version of our collision. It's just a deforming animation in a packed geometry. So we need an RBD deforming to animated node to turn our deforming animation to an animated animation. And that should now result in the fact that our sphere is moving, as we can see. But something is still not working. And that is, there's no destruction happening. And actually we've seen why, because obviously on purpose I made sure that my animation is so that my projectile will actually never hit my geometry. By the way, that is exactly the problem we talked about in the SDF video, only that we can't use SDFs here, we need actual substeps here. And the substeps we want to change here is not the bullet substeps, but of course the global substeps. And this is basically, this is why it says global, the substeps of the .NET that is inside of our RBD bullet solver here. So this is important to understand. Maybe let's set it to 4 or something. These global substeps will be applied to the static object that is inside here. So our sphere will be read in 4 times per frame. You should make sure if you do this that your sphere is also actually moving in those substeps. So keep in mind that you can always turn on, go into the settings and then turn off integer frame values, or in Houdini 19.5 it's actually simpler. There is a little button here, enable playback at fractional frames. And if you now go with your arrow keys through time, you can see that the sphere is actually moving in the substeps. If that's not the case, you might have to check what's going on here, where you lose the information. As we know, commonly that happens, for example, if you would cache that for some reason, then you might have to interpolate the geometry again. So always double check that you have the substeps that you need here. So let's turn this back off. And now let's see what we get with substeps of 4. Maybe we need more, I don't know. Let's try 4. And no, we don't. It actually breaks up. Now, okay, this looks different to what we had in our preview because it was a different setup, but at least we can see it works. So what we can do to adjust this is, for example, making sure that the glue around our pieces is a bit stronger. Maybe we went too low with this. So let's go back to our constraints in our RBD material fracture and let's increase that again 10 times. Let's see how this looks like. Interesting. It actually results in fewer pieces, which is usually a sign that the strength is too high. So let's go back a bit more, maybe to half for each and see what we get. And that's not bad. That I think is already pretty helpful. But if I wanted the cracks to, fly away further to the edges of my glass, remember there's always also the option to use our propagation iterations, which is something that we can always use whenever we use glue constraints. And in this case, we have a glue constraint. Unfortunately, there is no setting here to change the propagation iterations. And for that reason, we can actually use constraint properties, an RBD constraint properties node. There you go. And here we can actually change the propagation iteration, let's say to 10 maybe. Be careful though, what we now did is we changed or we overwritten the strength of the glue constraint. So theoretically it should not go through. Yeah, okay, so nothing happens because the strength is now too strong. Let's try to not override it. Unfortunately, you can't turn it off, but you can set it by attribute and then just keep it at strength and then put it to 1. So that means we take the strength that's already there and just multiply it with 1. So we're not overriding it. And now we should see, yeah, that we have what we had before, but actually I want more. So let's try a propagation iteration maybe of 30. Why not? Let's see what happens. Yeah, that's better. Now we start to get some impact that looks like something. Also what we can do, what I would usually try is just increase the substeps further. So for high velocities like this, I think this will give us more pieces, and I think we can already see a reaction there. Let's see what happens. Yes, we even get more cracks up there. So maybe that's also an option for you. So play around with the settings. You know, this is highly, as you can see, depends on your case. In my version, it looks like this. In your version, it might look completely different. So a lot of things you can play around with. The substeps, the propagation iteration, the glue constraint strength. So plenty of ways of getting exactly the behavior that you want. All right, so now that we're happy with this, let's finish this off by actually now adding again our frame, because the pieces should collide with this actually. So we can just merge the two together, and when we test this again, you can see now the blue frame has appeared, and we run this, it does seem to work. So at first glance, there doesn't seem to be any big problem. But just to keep that in mind, whenever you add any collision object, again, make sure you actually visualize under visualization the collision shape, and you can see again, like we saw before, this will create a convex version of our frame. So even though it kind of works here, make sure that when you have a concave object, use concave as a collision shape. So let's run this again. I don't think we will see a difference here. No, it's really, it is different, but it's not that it was worse before, but this way at least it's clean and stable. Also keep in mind, you might end up with, jiggling and jumping around. So the whole techniques that we looked at, like checking your collision padding, is of course a good idea here as well. So let's quickly do this under visualization, collision shape. You can see that the padding might be a little bit too big for our relatively thin glass. So under properties, let's lower the collision padding to 0.01. Actually, I noticed that lower doesn't work well. And this way, hopefully the whole thing should be more stable. And then of course we could, adjust the velocities and the radial velocities of our geometry with a point wrangle and so on. This is another topic, and we talked about this in the jitter fix video. So check that video again if you have problems with this in this example. Okay, so we could finish here actually, but if we would try to render this, we run into a surprising problem. When we fracture glass, because it is transparent, you can already see the fracturing before the projectile even hits. And this is a topic by itself, which is of course specific to glass as a material. And this is why I gave it a whole video, because there are a couple of techniques that Side Effects provides to us to solve this problem. So in the next video, we will take our example from here and look into how we render this so that we don't see the fracturing before it actually is happening when we render this as a glass material. But anyway, for now, I hope this is helpful. So thanks very much and see you later. Cheers.